Sorry about that. I had a slight technical difficulties here, and I've actually taken off the headset because it made me realize that there might have been some delay between my voice and the video, and that would drive me crazy. So the first 13 minutes, I'm really sorry. So let's get back. All right. So letter designations. Okay. So inductors, they're rated in L. Okay. And so when we say what is the inductance of the inductor, the question is in L, and the unit of inductance is Henry. Okay, so most of the time, especially in our labs, they're millihenry. They can be, very rarely will you see like a microhenry, but you do see millihenries a lot, especially in our labs. Okay, now henries, the the unit or the amount is based off the physical characteristics of each inductor. So each inductor can look identical, but maybe they have a core, maybe they don't. There's a ton of different looks. Okay, you'll see a number of them in our labs this week, and so here is what the physical characteristics that make up an inductor. So L increases by square as the number of turns increase. So if I take my wire and I rewrap it around here, okay, all right, if I have only a few, all right, it's going to have less inductance, and the more I come in here, the more I coil this, the more it will have. All right, the more spread out they are, the less inductance. The closer they are, the more inductance. The thicker the wire, okay, the larger the inductance. And is there a core? Now, a pencil does not make a good core, all right? But if there is a core in here, if you put like a nail in here or something else that has permeability, that will affect it. Iron filings, things like that. Some do, some don't. It totally depends on the application of the inductor, okay? Now, inductors in series. All right, so when we're trying to figure out henries, the total henries, all right, the total inductance of a circuit, all right, if that's the only question we're asking, we add them up just like we would a normal resistive series circuit, meaning you just simply add them together following this formula right here, okay? And let me go ahead and give you an example of that. If I have one inductor here and one inductor here. All right, let's say this one is 30 millihenries and this one is 90 millihenries. Well, that's pretty easy. My total is going to be, my LT is going to be 120 millihenries. Okay, now if I come in here and I drop a third, all right, inductor in here, okay, and let's say this one had 60 millihenries, all right, then my total goes up to 180 millihenries, okay, so it's pretty straightforward and pretty easy to work with, okay. Now, if we have inductors in parallel, this is what we're going to deal with. This is going to act just like the reciprocal. And this one can be a little more tricky because the numbers are so small. Typically, when you're doing the reciprocal rule with resistors, all of them are above 1. Okay? So the reciprocal numbers are a little bit easier to use. But when you're dealing things that are, in the millihenries and things like that, my personal opinion is you should just keep everything in millihenries, in henries, or microhenries in that rare example. All right. So in a parallel circuit, all of the normal rules to of a parallel circuit still work. Meaning that if you have two of them that are at 2 or many of them that have the exact same inductance values, you would just take that value and divide it by the number. Okay, and I'll show you an example of that here in a second. We use a reciprocal rule, or we can do the product over sum, which is not something that I'm typically a big fan of, but you can use it if you want, being displayed right here. Okay, so let's go ahead and walk through the parallel circuit here real quick. All right. So, all right. So, let's go through the first one. So I have one, we'll just start off with two inductors. All right. Now let's say this one is a 60 millihenry, 60 millihenry inductor. Okay. Well, in that case, I can just use this rule here. I can just take 60 millihenries divided by 2, which would give me 30 millihenries. Okay, which is pretty easy and pretty straightforward. Now, that rule would hold true if I came in here and I added another 60 millihenry inductor. Okay, then I would just be dividing it by 3. Okay, and my answer would come out to be 20 millihenries. Okay, now the next cool thing is, the next one, if I wanted to do the reciprocal formula, all right, so let's say each one of these was different, okay, and we'll just do 2 for simplicity purposes. So let's say this was, we'll just keep this 60 millihenries, and this was 100 millihenries, okay? Sorry, my camera keeps kind of zooming in and out there. It doesn't like my motion, I guess. So my formula would be 1 over 60 plus 1 over 100, and then take the inverse or the reciprocal of that. Okay? And I know you guys know how to do that, so I'm not going to you're not going to make you watch me type that in. But my answer would come out to be millihenries. Cool? All right. So, bring this back up. All right, so let's do a quick review of DC current in, let's do a quick review here of Lenz's law in a DC current, okay? And then we'll start moving on to the AC stuff, all right? So, DC applied to a coil creates a single short event called back EMF, okay? And that is the creation of that electromagnetic field, all right? It creates that electromagnetic field, and that fights back what's happening there, okay? Then once the current is steady, the back EMF disappears, the magnetic field is held steady, okay? There's no longer motion between the magnetic field and the coil of wire, okay? Then, when the DC in the coil turns off, okay, so the power shuts off, all right, that magnetic field collapses, and that creates that kickback voltage that we talked about that goes in the same direction as the current that initially created it, okay? And so that kickback voltage disappears when the current in the circuit drops to 0, which happens very, very quickly, all right? And now, a normal question might be as well, how fast does that happen? Okay, or how can that be calculated? And that can be calculated the same way as all of the universal time curves that are out there. And we typically aren't as worried about this with inductors as we are with capacitors, just because of the way that capacitors are used and inductors are used. But if you wanted to understand it, you could calculate it out that same way, where it takes 5 time constants to get to the theoretical full charge, okay, or full electromagnetic field, all right, and and every time constant, it would change from 0 to 63.2% of the total current that is going to go through there, okay, and then after 5 time constants, we're at 99.8%, and we say that's full. Okay, theoretically, it will never get there, but after 5 times, whoo, high five, we say that we're good, okay? And then it works the opposite on the collapse, all right? All right, very cool, very cool. So, I'm going to go ahead and pause this real quick, and we're going to see how this video came out, and then we will go to the really important stuff for this particular lecture. How does inductance, how do inductors react when they are with AC? All right, so here we go.